using the appropriate substitution. So typically the u is going to be what is the argument of a trig function, what is in parentheses, what is the argument of a square root. Same kind of reasoning that we used when we did the chain rule. So for example, this one, I've got a cosine function, and I can't integrate the cosine of x squared. It needs to be the cosine of just one variable. So I would choose u to be x squared in this case. So why don't you go through, all the way through to this one and see if you can figure out what u would be on your paper. So again, it's things that are in parentheses or things that are in the square root or the argument of a trig function. There's an exception to that you'll see later. So I'll let you think about. And what I'm going to do to give you a little hint here on this one is remember that the sine cubed of x is the same as the sine of x cubed. So now you see something in parentheses, so that should lead you to choose the correct u. So this last one, a little tricky because you would say, okay, yeah, I can rewrite the secant to the 8th power. Secant 8x is the same as secant of x to the 8th power. And you could just leave it as that and say u is the secant of x. But it's actually better to use the trig identity that secant is 1 over the cosine, so it becomes the sine of x over cosine of x to the 8th power. So at that point, it should be easier to recognize what u is. Okay, so that's the first thing you have to do. So let's go back to the beginning. The second thing you have to do is you have to calculate du. So du, all you do is you just take the derivative like you normally would using the rules that we have, and then add a dx onto the end of it. So the derivative of x squared is 2x. Add the derivative. Again, what this is doing, it's basically putting the original equation in what we call the differential form. So the differential form means that this part becomes du, and this part is the derivative. And again, yes, from yesterday, if I did u prime of x, equals 2x, and then I wrote u prime of x is du dx, and then I multiplied by both sides by dx, I get the same answer. But it's easier just to think of it, to go from here to here by just taking the derivative of that and then just adding the dx instead of having to, separate it and rewrite it like that. So just go to the next ones and take the derivatives of the right-hand side and tack on a dx. So I'll give you a minute of head start there. So somehow I was reading the New York Times on my cell phone this morning, and then I looked at Facebook and I noticed it said I posted an article, which I don't remember doing, so I accidentally the article's about gun control. Luckily, I think I stopped following all my conservative friends, so they probably I won't get too many people writing back saying it's not guns that's the problem, it's mental illness or something like that. Prepare for the onslaught. It's basically saying the reason we have so many mass killings in the U.S. is because we have so many guns. There's correlation between the number of guns you have and the number of people you kill. Don't ask me why I did that. Okay, everybody have any questions about what I do? Well, let me just go back here since you may have been working. So the derivative of 10x minus 3 is just 10, and then you add the dx. The derivative of 4 minus 9x squared, this goes to 0. You get negative 9 times 2 is 18. You reduce the exponent by 1, multiplied by dx. Here, I rewrote it as x to the 1/2 power plus 1. So this goes to 0 when I take the derivative. So you get 1/2 times x to the minus 1/2, and then I rewrite it as this with my dx on the end. Here, the derivative of the sine is the cosine of x multiplied by dx. Here, the derivative of 10x is 10 multiplied by dx, and the derivative of the cosine is minus the sine. So it's minus the sine of x dx. Okay, so that's the second step. Now the next thing you do is you look at the original equation and see if I've got, this part is going to be the part that involves u directly. So I'll have the cosine of u if I make the u substitution. The rest of it is x dx. So what I don't need 2x dx, I need x dx. So you take this expression, you always divide by a constant or multiply by a constant. So in this case, to get just x dx, I need to divide both sides of this equation by 2, and I've switched the sides so I can make the substitution. So look at the original equation here and see what I have. See, for example, here I just need dx. So because I just need dx, I'm going to take the previous equation and divide both sides by 10. So this step basically involves dividing by a constant if it's appropriate for the substitution. Because what I'm going to do is, I'm going to substitute for u, I'm going to put that in here. And for x dx, I'm going to put that in there. So this part will use this substitution. So do that for all of them if it's appropriate. And some of you won't have to do anything because it's already in the appropriate form. Okay, so let's look at them here. So all I need here is x times dx. So I take this, divide both sides by negative 18. So I get my x dx substitution is du divided by negative 18. Here I have dx over 2 times the square root of x, which is exactly what I have here. So I don't have to make any changes. I can just substitute du directly. Same with this one. I've got cosine of x dx as my stuff that's not involving the terms that are direct u substitutions. So this part will just be du. Here I've got dx. Here I've got 10 dx. So I solve for dx. dx is du divided by 10. And then the last one, I've got du is equal to negative the sine of x dx. Up here I have the sine of x dx. So I just multiply both sides by negative 1. So I get the sine of x dx is equal to negative du. Okay, so now we're going to make the substitutions into the original equations. And so we're going to rewrite the original equation in terms of u. So in this case, the cosine of x squared becomes the cosine of u. And the green part, x dx, becomes du divided by 2. So that's the next step, is just to make the substitutions. Don't rearrange anything at this point. So here we'll have, for dx, we'll put du over 10. For 10x minus 3, we'll put u. So this one becomes, the term of parentheses is u. So I get 1 over u squared times dx. dx is du divided by 10. Okay, the next one, this is going to be, these two terms always group into the du term. So we get 1, we're just going to have 1. If I move this over here, it's going to be 1 over the square root of this thing, which is u. So I get 1 over the square root of u times du divided by negative 18, which is what x dx is. X dx becomes du divided by negative 18. Here, this is u, so that's u to the 4th power. This dx over 2x, 2 times the square root of x is du, so that becomes u to the 4th du. Here, sine cubed of x, sine of x cubed, that's going to be u cubed, and the cosine of x dx is the du part. Here, the integral of the secant squared is the tangent. That's why we didn't do anything with changing that to the secant of something squared. So in this case, 10x is equal to u, so it's the secant squared of u, and dx is du divided by 10. And then the final one, for cosine of x, we substitute u. So we get u over 1 over u to the 8th. The sine of x dx is negative du. Okay, so those are the substitutions. Now before we integrate, we're going to do one final step, and that's just to factor out any constants. So I'm going to factor out my half here. So go ahead and do that for the other ones. Factor out the constants or the signs. So if there's a negative sign, go ahead and factor that out as well. And you'll understand why I'm doing that. I mean, ultimately what we're trying to do is we're trying to get them to match exactly with the equations on the sheet that I handed out. And there's no negatives involved and inside the integral, and there's no constants involved. So that's why we want to just go ahead and factor out the constants at this point. I know some of you probably could do that in one step, but for right now, let's do it in multiple steps. So. And some you don't have to do that because there aren't any constants. Okay, so there they are. These two didn't have any constants, so we didn't have to do anything to them. Anybody got any questions about anything so far? Okay, so now all you have to do is, if you remember what the integrals are, you can go ahead and do them. But if you don't, well, for some of them you're going to have to rewrite. So here you're going to have to rewrite this as u to the minus 2 power du. So anything that's in the denominator, go ahead and rewrite those first as negative exponents in the numerator so that you can then use the power rule formula, which you can see is pretty much, except for a few cases, is what we end up doing, is we just end up doing the simple power rule, which most people can handle. So that one I'm going to make negative 2. Let's see what else I got. This one I need to rewrite as the integral of u to the minus 1/2 power. So I've converted that to the u to the 1/2 and moved it to the numerator. So that's a power rule. That one's fine. That one's fine. That one's fine. And then this last one you need to rewrite as u to the minus 8th power du. Okay, so go ahead and now do the integrations. And remember, what happens is when you get when you do the integration, the integration sign disappears, so don't leave it there. The du disappears when you integrate, and the arbitrary constant appears. So in the next step is you're going to drop the integral sign, you're going to drop the du, and you're going to add c, the arbitrary constant. Oh, you're looking for your formula? Yeah, the integral of the cosine is negative the sine.
Okay.
You get the negative, it's a negative, the integral of the cosine. No, it's right. It's just the sine. Sorry. It is the sine. It's just the sine. I always get confused with that. So yeah, the integral of cosine is the sine, not the negative sine. Okay, so let's just check your answers here. So here, you add 1 to the exponent, divide by the new exponent, add your arbitrary constant c. While we're at it, let's go ahead and rewrite it. So that we'll take the negative sign out front, and we'll move the u to the denominator. So we get negative 1 negative, I guess that's a 10, not an 8. Sorry. So it's negative 1/10, and then this is u to the first power in the denominator. Okay, so that's that one. The next one, again, we're going to have to do a little cleaning up. If you multiply the denominators together, you'll get 18 times a half, so that becomes 9. So you get negative 1/9, and u to the 1/2 is the square root of u. Okay, next one. That one's, we don't have to do anything with that. It's good. That one's fine. This one's fine. The last one, just got a couple of extra negative signs, so the two negatives cancel out, and I'd move the u to the -7th to the denominator. Okay, so we've got it in. We've cleaned it up as far as making sure that we don't have any negative exponents, and that if we've got anything raised to the 1/2 power, we convert that to a square root. Okay, and then the final step is just to substitute u back in. So we go back to our, by this time we've forgotten what u is, at least I always do. And so we go back and look what u is, and then just plug that into the solution. So this is going to be 1/2 the sine of x squared plus c. So go ahead and do the rest of them. Stick u back in there. Okay, so let's go back and see if you got them right. So, so the second problem, you get negative 18 times 1 over u. U is 10x minus 3. Add your arbitrary constant c. The next one is negative 1/9 times the square root of 4 minus 9x squared plus c. The next one is just the square root of x plus 1 to the 5th power divided by 5 plus c. This one becomes the sine to the fourth of x over 4. So I got the sine of x to the fourth. I went ahead. If you have this situation, we ended up taking this form, going to that form, so we could recognize that this was going to be u. You can kind of go back the other direction to go back to the compact form. So sine to the fourth of x over 4 instead of the sine of x to the fourth. It's the same thing. Then we get 1/10 the tangent of 10x plus c. U is the cosine of x here, so you get 1 over 7 times the cosine of x to the 7th. And I went ahead and rewrote this as the cosine is 1 over the secant, or the secant is 1 over the cosine, so I moved that to the denominator. Typically, if you have a trig function and you can convert it back to a term that results in the term being the numerator, you usually go ahead and do that. So if you divide by the sine of something, then you change that to the cosecant. If you divide by the cosine, you change that to the secant. If you didn't do that, I probably wouldn't take off points for it, but that's probably the best way of doing it. Okay, so that's how that works. The next thing we're going to look at is these are all indefinite integrals. So the question is, what do you do when you do an indefinite integral? And you could say, well, I'll just take the indefinite integral and then I plug the numbers in. But there's actually a better way of doing it, which I will explain now. So we'll go back to the lecture notes here. So that's the next part of the handout, but we're going to go over the material first. We probably won't get to actually doing anything, so you can put that away probably for today. Okay, so here's an example. It's a definite integral because it has limits. So in this case, the result is we want an answer. In the case of what we just did, we wanted an answer, which was an equation, and we wanted the equation in terms of x because the original equation was in terms of x. The thing about when you have a definite integral involving something where you have to use u substitution, you don't necessarily have to substitute u back in. What you do is you rewrite the equation in terms of u, and you rewrite the limits in terms of u. And that means you don't have to go back and resubstitute. It just makes it easier. So it's pretty much the same deal as we did before. So in this case, I would choose u to be x squared minus 1, because that's the expression in the parentheses. And my du would be equal to, would be the derivative of this. The derivative of x squared is 2x. I tag on my dx, and then I look to see what I've got in my original equation. Well, the original equation, I have 2x dx, so I don't have to do anything here as far as dividing by any constant. Now, the step that we haven't done before is we're going to change the limits. So instead of having the limits in terms of x, they're going to be in terms of u. So the way you do that is you just plug in the values of x, which are the limits, into the equation for u. And see what you get. So usually what I do is I say when x equals the lower limit, in this case, which is 1, I just plug in x equals 1 into the equation for u. So instead of what I'll get is I'll get 1 squared, because x is 1, minus 1. So my u limit is 0. And then I take the upper limit, so when x equals 3, u is going to be equal to 3 squared minus 1, which is 8. So when I do the substitution, like I did over previously, I do two things. I make the substitutions for these parts of the expression. So I'll get the square root of u, and here 2x dx is du. But I'll also change the limits. So instead of integrating from x equals 1 to x equals 3, I integrate from u equals 0 to u equals 8. And I'm going to explicitly put this up here just to make sure we understand that. So that's x limits. This is u limits. So at this point, I don't have to substitute back in anything because I'm just going to do the rest of the problem in terms of u. Okay, so let's do this. So we first, before we integrate it, we have to rewrite the square root of u to the 1/2 power. Okay. Then we integrate. So we add 1 to the exponent, divide by the new exponent, add our arbitrary constant c, make sure there's no du and there's no integral sign. Actually, we don't put a c, sorry, erase that. It's a definite integral, so we draw the straight line and we go from 0 to 8. Before I plug it in, I'm just going to take the reciprocal of the denominator. So it looks like that. I haven't changed anything. So do the definite integral. I evaluate my function at the upper limit, which is 8, and I subtract the function evaluated at the lower limit, and I get an answer, whatever that is. So I'll plug it in my calculator. So what is 8 to the 3/2 power? 8 is 22.6. So I get 2/3 times 22.6. So times 2 divided by 3. So the answer is 15.08. So that's the area. And it's the area underneath this curve between x equals 1 and x equals 3, but it's also the area under the curve u to the 1/2 power du from 0 to 8. Now I could have gone ahead and substituted back in, and so the other option, so this is plan B, what I could do is I could take my equation here and plug back in this expression for u. So that would be x squared minus 1 to the 3/2 power times 2/3 evaluated between 1 and 3. And I'd get 15.08. I get the same answer. So the advantage of doing it this way is I never have to plug back in u, and therefore I don't. Typically, u is simpler than what u represents. So u is just a single variable. Here, u is x squared minus 3. So x squared minus 1. So at some point, I've got to do this. I've got to evaluate this. And when I evaluate it here, it's a lot easier than making a chance of making a mistake. So, I mean, either way is fine. I used to teach it this way, and then I decided that I actually like that way better. So that's the way I'm going to see if you guys can do it. So there we go. Okay. Yeah, so why don't we try that one? The graph on the right will be, you'll understand that when we finish it. So what you're going to do is you're going to you're going to let u equal x cubed plus 1. Then you'll calculate du, and then you'll say when x equals 1, u equals something, and when x equals 2, u equals something. That's changing the limits. So see how you can do that by yourself. Oh, one thing, this is the first problem that we've had this situation, is typically, in the last problem I didn't factor out the 2. If we go back to this previous problem, I didn't factor out the 2 initially because I knew this was going to happen, but that doesn't happen most of the time. So it's better to before you do anything is to factor out any constants. So because unless this constant matches the one that is here exactly, then it gets confusing. So it's better just to factor out the constant to start with. And what you'll end up doing here is you'll calculate du, but you'll see that you need x squared dx as something. You'll have that factor of 3 that you'll have to take into account. Don't forget your dx. And then you're going to want to divide by 3 to get x squared dx, so you can make that for x squared dx. You can make that substitution.
Divide by 3.
Yes, ultimately, yeah.
Okay.
Yeah. If you see it, you don't need to put that intermediate step. The intermediate step would be to factor this out, which actually make sure you erase that because you factored it out, so it shouldn't be there anymore. Yeah. Does anybody get my answer? Good. Okay, so we let u be the argument of the square root, x cubed plus 1. The derivative of x cubed is 3x squared. Tag on the dx, derivative of that is 0. So I factored out the 2 so that I had just x squared dx. So to get x squared dx out of this, I divide both sides by 3. Then to change the limits, I use my definition for u. So when x equals 1, u equals 1 cubed plus 1, which is 1 plus 1, which is 2. And when x equals 2, you get 2 cubed plus 1, which is 8 plus 1, which is 9. So using this substitution, I get the square root of u. The x squared dx becomes du divided by 3. I factored out the third in the denominator, so I get 2/3. The integral from u equals 2 to u equals 9 of u to the 1/2 power du. You add 1 to the exponent, divide by the new exponent. I took the reciprocal of this, which is 2/3, multiplied by 2/3, gives you 4/9. And then I finally plug in the limits. So I've got 4/9 times u evaluated at the upper limit minus u evaluated at the lower limit. And if you do that, you get that answer, if I did that right. So that is how that works. So let's look at, well, I told you to put the sheet away. Let's see what we got here. How many of these do we have? We have 5 of them. So since we'll work on those next time, but I'm going to do one more thing. So I'm going to give you a little intro in the next 8 minutes. Okay. But actually, let's look at this graph. So this graph is the two functions that I was talking about. This is the function, the original function, which was 2 times x squared times the square root of x cubed plus 1. If I plot that function, it looks like this. And if I go between x equals, if I look at the scale, here's 1. So this blue hashed area represents the area underneath the curve, the original curve between 1 and 2. So that's what we were trying to find. This curve, this light blue, the blue curve, is the u equation, which is the square root of u. It's the square root of u, but with the proper factors. So that's 2 times the integral from 2 to 9, which are what are the u limits of the square root of u. So if you plot the square root of x and you look at that on the graph, it's this equation. And it turns out that the green hashed area is exactly equal to the blue hashed area, which, and the green starts here because u is integrated from x equals 2, which is here, to x equals 9, which is there. So yeah, the area from here to there under this blue curve is the same as the area from 1 to 2 under the red curve. And it's true. Okay, so I'm not asking you to tell me whether you think it's right or not, but it is true. So it's the interesting thing is that the curves look very different. This one's going up. It's getting larger as x gets larger. This one's actually kind of leveling off a little bit. So I always thought that was kind of cool that those areas are exactly the same, even though the shapes of the curves are quite different, at least in the intervals that we're talking about. Okay, I thought I had another kind of problem. Gotta figure out where it is. Maybe I skipped over it. Yeah. Well, let me just check some here. Yeah, I thought I did that. That's okay. Just don't worry about that. I can't remember what section 6 is. No, it's not section 6. Okay, I think I can make one up. So this is just a different kind of problem. If I have the square root of x squared, x plus 1 times x dx. So there's another kind of problem that they talk about in this section. It uses a different type of substitution process compared to what we've been doing. And I usually include one of these on the test, so it's worth going over. So in this case, you look at it and you say, well, if I chose u to be x plus 1, the derivative of u would be just 1. It would just be dx, du would be dx, and I've got that extra x in there. So I can't use the normal procedure up to this point as far as substitution. So this is just saying there's other ways to do these things, and that's what math professionals and scholars have done all of these years, is try to figure out how do I convert these equations into the functions that I have in that table so that I can integrate it. So the way these work is you let u still be the argument in the square root, and du is still the same kind of procedure. So the derivative of x is 1, and you multiply it by dx. So du is dx. But what you can do is you can take the u equation and solve it for x. So I take this one and I solve for x. So that says x is equal to u minus 1. If I subtract 1 from both sides of this equation. And now you can see I have 3 substitutions. For u, I can make that substitution. Or for x plus 1, I can use that substitution. For for dx, I can make that substitution. And for x, which is this thing that I didn't know what to do with, I can use this substitution. So what you end up with is for x, I put in u minus 1. For the square root of x plus 1, I have the square root of u. And for dx, I have just du. So now I've rewritten this in terms of u. And you might not think it's any better because it's got about the same amount of terms. But if I were to rewrite the square root of u as u to the 1/2 power, and then I were to multiply this out, so if I distribute that u, you add the exponent. So here this is the first power. So u to the first power times u to the 1/2 power is u to the 3/2 power. And then you've got the second part, which is just 1 times u to the 1/2 power. Like that. And now these are just power rules. So the integral of u to the 3/2 is u to the 5/2, add 1 to the exponent, divide by the new exponent. Here's the same thing, add 1 to the exponent, divide by the new exponent, add your arbitrary constant c. Take the reciprocal of the denominator. So it looks a little nicer. And then finally, you can go back and do your substitute u back in. So you get 2/5 x plus 1 to the 5/2 minus 2/3 times x plus 1 to the 3/2 plus c. So there's your answer. So it's it's a very special case. It usually involves the square root of something times something involving x. So I could have x squared here, and I could still use the same substitution. But that's kind of the form it. And typically, when I put it on the test, I'll say use the second type of u substitution. So you don't have to guess which one to use. You just have to know how to use the procedure. And the only additional thing that you have to do is typically, again, you pick whatever's in the argument of the square root as u. But to finish it out, you've got to solve this equation for x and then substitute it in. Okay, so I don't know if I've officially assigned homework for this section, so I'm going to do it now if I haven't. And actually, there's a whole lot of homework for this section. So there's actually 2 parts, but you can just write them all down at one time. So this was what I did initially, and then I was like, you need more practice, so I came up with this after a few years. And the reason there's so many problems is because super critical to understand this procedure because we're going to be doing it again and again and again and again and again.